So yeah, we're going to be going through a bit of a Mathematica tutorial, particularly focused on some of our AI and algorithms. So that's going to be like the main focus of today. A bit about us, if you haven't heard. So we are Wolfram. We are kind of like this long-standing tech company. We've been around for 30, 40 years or so, and we've been doing a lot of things in the kind of like computational space for a while now. And this is like, we do a lot of, consultancy type things. So that's what I'm like especially involved with. I, deliver kind of solutions powered through our proprietary technology. So we have, the Wolfram language, and with this kind of powers, a bunch of different products. And often, I'm involved with, delivering computational solutions in the form of applications which we give to our clients and customers. So yeah, so what's kind of what we're going to be talking about today. We're going to be introducing you to the Wolfram language and the kind of like hopefully I'm going to show off some of how fundamentally easy using going through some AI and kind of general algorithmic stuff is with the Wolfram language. So this talk, especially what I'm going to be doing is, so first I'm going to give a bit of an outline. So I'm going to go look at some machine learning in the Wolfram language, maybe like just give a bit of a refresher of like what we mean by machine learning, then show off a few like quick examples of how we can do that. Then we're going to look at a classification workflow, prediction workflow. Then we're going to touch on a bit of neural networks and then look at some of the like integration with LLMs we have just within the Wolfram language. So, right, when we're talking about machine learning, we're kind of, machine learning is this kind of subsect of AI. And, by artificial intelligence, we're talking about where, computers are kind of imitating humans to solve a particular problem. They're using reasoning to solve things. And so machine learning is a subsect of that. And so within machine learning, we kind of have this computer model where it's kind of learning from a set of data. And by a model, we're kind of talking about a program that has parameters, and the whole learning process is, tuning those individual parameters to fit a particular data. And then we can go ahead and do some further things like prediction, classifications, etc., etc. So there's a bunch of different kinds of learning. We've got, supervised learning, where we've got this like ground truth associated to from inputs to outputs, and this kind of ground truth is kind of the supervision, if you will, that we're giving it. We're kind of telling it this is what to do with this given output. So this is particularly useful for kind of object recognition, image recognition type stuff, and it's the most common type of machine learning that we utilize in Wolfram language. When it comes to unsupervised learning, we're kind of just effectively throwing data at a model and hoping it to kind of find useful patterns in this, unlabeled data. So this is good for things like speech synthesis. We've also got, reinforcement learning, where we're kind of closing the feedback loop of supervised learning, unsupervised learning, kind of joining the two. And so this is kind of useful for like adaptive learning type tasks. So playing a game, so making AI to like play chess, for example, is a good example of reinforcement learning. So other types of tasks we can do, so classification of images, sounds, text, etc., is a pretty standard thing. Predictions of variables and data sets, very powerful thing to be able to do. Real life data is never as clean or precise or even present as it is in some of those like nice online data sets you have. So being able to predict data is always a powerful thing. You can even augment the ability of your models by, stuff like imputation, where you have a missing variable in a data set and you predict that so that you can then use that entire row of data rather than just writing it off as missing data. Also, things we might be doing, some kind of text translation. So here we've got like going from English to French, but we might be, predicting some kind of time series. We might be doing some general anomaly detection. We might be doing some data clustering, might be solving a maze. And like these are all general tasks which are pretty easy to be done in the Wolfram language. So This slide, we're going to be kind of going over a bit about the general Wolfram language itself. So the most common environment you're going to be using Wolfram language is a notebook environment. So this is a special kind of environment. This is a presentation environment, but the general environment looks like this, and it's kind of like it works very similar to a Jupyter notebook environment if you guys have used that before. But it's pretty simple. If I want to create a function that squares everything from a range of 10, I can go ahead and do that. And it's this nice, you know, Jupyter notebook-like environment. I press Shift Enter to evaluate my code, and I get a nice result for it. So the kind of language itself is that we define it as like symbolic, and it's also this like numeric computational language. But to be honest, it doesn't just fit one paradigm of programming. To be honest, it's functional language, and we can do lots of different powerful things with it. It's very nice. Um, Also within the Wolfram language, we have this like natural language understanding. Potentially, if you guys have heard of us, it's probably through Wolfram Alpha. Um, and you have access to this like just within a notebook. If you want to, you can just search Wolfram Alpha for stuff by pressing the double equals. If I want to learn about the chemistry, I'm able to go ahead and get some information about chemistry. So I could go ahead and bring that all into this environment pretty seamlessly, which is pretty cool. We also have access to state-of-the-art algorithms within Wolfram language. So if I want to do any kind of specific kind of computation, I can do that very easily and seamlessly. We've kind of like it's not just algorithms, but we've curated a lot of different kinds of data sets, and I guess one of our like core ethos is providing computational knowledge-based tools to do a lot of different things, but especially useful for data science and AI machine learning are things we're pretty powerful at. We also have a bunch of different built-in data. We support lots of different data formats, and we have this like seamless deployment to the Wolfram cloud, which we'll look at an example of in a bit. So in general, we are like we can be described as a functional language. We operate through functions, and general function syntax is, it has a head, which is going to be describing what the function is actually doing. And then you have the square bracket notation, and within those square brackets, you have the parameters that you are applying the head or the function to. And you also have the ability to provide options to the function. So these are not required parameters, but particular options. So if I'm doing some kind of plotting function, the option might be to change the color or something like that. So yep, and so pretty fundamental to the core programming. So we've got these core data structures, very similar to other languages of lists. So we can have this basic list of 1, 2, 3, 4, etc. And there's no limit to how deep these lists can go. We can have lists of lists, lists of lists of lists, etc., etc. We also have associations. So this is effectively the same as like a dictionary in Python. It's this key value mapping, which is very powerful and useful in general programming. Also, so within Wolfram language, we have access to this kind of like powerhouse function data set. So this just, if we feed it some raw data, we can go ahead and get this nice like tabular information about this data, but is a pretty powerful way to kind of get a holistic overview of some data. So we're going to be primarily talking about like machine learning within the Wolfram language, and so within the Wolfram language, you have access to these, very high level functions. It's a very high level language. You almost have to write very little code, and you can do an awful lot with it. So we have these incredibly powerful, like just built-in functions like classify and predict, which to an extent just automates the entire process of classification or prediction, all for you. So I can just pretty much throw some data at it, and it quite often builds a very powerful classifier, predictor, and this is going to be based on um, some kind of a bunch of different ML methods that we have created and like done for you. So you as the user can just, as I said, just throw some data and build these powerful predictors. We also have a bunch of other powerful things, but I guess the main thing I'm trying to like show here is that, with these like high level functions, it makes machine learning like very in general like easy to use, very automated, and often the names are defined. The function names are kind of more named with their task in mind rather than the specific method itself. So within classification, there's many different algorithms you can use, but we kind of just group them all together in this classify function. So also within the Wolfram language, and we will look at a little bit as the neural network framework. So this is, a very powerful thing in of itself. It's very flexible, model oriented, and it also has you have access to this high performance. So we can even, you know, specify the training of the model to be done on a GPU. We have this nice, pretty seamless integration with CUDA, which is pretty cool. But obviously that's only going to work on a machine which has a CUDA card in it. So I'm currently on a Mac, so I can't use it. But that's pretty cool. So let's look at a few quick examples of just that the you know how we can actually go ahead and use some of these functions. So here I'm using this classify function. Using telling it I want to classify a particular language, and then I'm operating on this kind of language. So it just provides this seamless ability to do that. I can also go ahead and give it some other options, so some of the top probabilities, and this particular example, it's kind of telling us it's pretty sure that it's going to be English. Yeah. So also another thing we want to do is some kind of image identification. So here we can kind of assign to these symbols here these individual images. So that's a nice thing about Wolfram language. You can kind of go in and out of different data types very easily. Like it's a very tolerant language to what you want to do. Like I can throw in if I wanted to, I could have a list of an image, a floating point number, or a rational number, which is another cool thing we have. So this is kind of we have 8/3. This isn't going to be turned into the floating point yet. We have this notion of rational numbers, so which is powerful for when you want to do like kind of symbolic type integration where you want effectively an infinite precision. But that's all pretty cool. So what if I can also go ahead and use this image identify function here over these assigned symbols using this map operator. This is the shorthand form for kind of going through a list. And this built-in function is able to identify this as a grey wolf and this as a lime, which is pretty cool. So this is, yeah, just a function that we have kind of curated. I think we're actually going ahead. We created a neural network for this to go ahead and do this image identification task. Also, you can go ahead, you're not limited by just this particular image identify function. We can also go ahead and get up some of another neural network. We have, so I mentioned earlier, we have, we've been curating data algorithms, in this case, neural networks for many years. We can go ahead and pull in a Google Lenet neural network. And then we can go ahead and do the same thing. We can map that to this Wolf and Limes and see what we get. And this one has outputted this as a lemon, which is slightly incorrect, I believe. But it's just nice to see this like seamless integration of external neural networks that you can go ahead and pull in with NetModel and then apply to our images, our image data. Also some nice quick examples you can do. So we can do kind of image restyling type things if we want to redraw the Mona Lisa in the style of Kandinsky. We can do that. So we're kind of mapping this Mona Lisa picture to this style. And we can also go for a Mona Lisa in the style of Monet. It's just, very seamless, only one line of code to do with it, what is like arguably a very complicated AI type task. Also, we can kind of like deconstruct text itself using this text structure function to go ahead and kind of like do some natural language processing of this sentence. Other things we might be doing, so kind of more data sciencey type tasks on some string data. So we're getting some data from Wikipedia on the moon. Then we're going ahead and we can go ahead and get some quantities mentioned in the individual Wikipedia text. So we're going to go ahead and run that. And hopefully it doesn't take too long, but maybe I should have done this earlier. And eventually it will, I actually have bought this. Give it another second. Yep, okay, finally we've gone ahead and got all these different quantities mentioned in this Wikipedia data, and then we can go ahead and do some general data science where we're counting all the cases where we have nouns in this data here. We're going ahead counting that and then just taking the 10 largest of those. So other things we can do, general anomaly type detection things just with one function. Then we can go ahead and get a random sample of things from the MNIST dataset. I think this is just mappings of images to ground truth, like say hand-drawn zeros to zeros, etc. We can then go ahead and make this detector function and then use it to identify the anomalies in this list here. And it's gone ahead and done that correctly, which is pretty cool. Right, so what we're going to do here, we're going to go walk through a classification type task. So this is, a very important part of machine learning and, in data science in general. So what you're going to want to do, you're going to kind of want to prepare the data. Then we're going to want to create a classifier, train the classifier, test the classifier, and we can also, measure the accuracy of the individual classifier itself. So what I've got here is I've got this kind of pre-baked in data set of a bunch of images of Guardians of the Galaxy characters. Then I've got a list of the actual characters themselves. What I can go into do here is pre-process the data to get up I think we're making the kind of ground truth mapping of Gamora to Gamora, Star-Lord to Star-Lord, etc., etc. Close that. Then we're going to do, one of our, classic things that we do in ML type problems. We're going to separate out our data set into training data and testing data. So normally it's going to be about 75% training, 25% you're going to use for testing. So we can go ahead and do that. Now, this is where I'm going to show off like one of the powerhouse functions, classify, where we just go ahead and evaluate that, where we go ahead and like actually create this classifier all for you. So this is, you've got a little peek into the training process itself, which we can look at a little bit more, and then we can go ahead and test this function which we have just created on some unseen images. So here it's correctly identified that as Rocket Raccoon. We can go ahead and pull out some of the, obviously with ML type problems, we're not ever going to be 100% accurate. It is more, it's a kind of workflow based in statistics. So, when we have that, we never get 100% accuracy. So, we could be getting a lot of different things, and these are the potential things that we might be getting. So here I'm going to go ahead and create a little anonymous function where we are slotting in some of the images, and then we are also slotting those into this classifier we've made, so we can kind of get a general view of how it's doing a bunch of different data on a bunch of different examples. So here it's identified that as Groot. That's not right. And so you see it's not done like perfectly. So what we can do is some nice thing that's baked into kind of ML things with Wolfram language is we can get this like general classifier measurements on our individual classifier where we also supply it this testing data that we made earlier. So this kind of gives us a nice holistic understanding of what we've been doing. So we've used the logistic regression method. We've got 20 examples of testing, so the accuracy is 75%, and giving this whole general information and this nice confusion matrix infographic, which is very powerful for if in this case, so we've got 5 examples of Gamora being correctly identified, Groot correctly identified many times, but here we've got one example of Star-Lord miscalculated as Gamora. So, with these confusion matrix type things, we can, be like, oh, we didn't get Gamora particularly right many times. So this can infer our retraining of this particular ML task, this particular classifying task. So yeah, it's just a powerful, seamless way of doing that. So again, we can pull those out individually. We can get the accuracy, confusion matrix plot. If we want to know the worst classified examples, and the best classified examples, it's all pretty just very seamless and nice. So we can also do some kind of like prediction type tasks. So let's go ahead and pull out some example data. So here we've got just baked into the environment itself, just this machine learning Titanic example data set. So it's a nice way to kind of seamlessly work with data so that we can, if we wanted to learn more about machine learning, we can go ahead and do that. So we've got this kind of mapping of passengers in the Titanic. They were first class, their age, their gender, and whether they survived or not. And we've got that for about 1,300 people. So we can go ahead and if we wanted to create a predictor, we can go ahead and so what we're doing here, we're kind of restructuring that data where we have converting this pattern into this pattern. So we originally have the data in this format, but then we are going and so this is kind of like pattern matching and replacement, which is a big thing in Wolfram language. So we're kind of going from one data format to another, and then we are then using this predict function to create this Titanic predictor. So with that all done, we can go ahead and feed it a a class type, a gender, and whether they survived or not, and we're asking it here to infer the age. So that's all pretty cool. So one nice powerful thing again about Wolfram language, it's got this like seamless integrated deployment possibility. So if we want to make a Titanic classifier, so we were just operating on the same data, the like mapping of class, age, gender, whether they survived or not. We can create this classifier. We can go ahead and use that again. We can generate a list of probabilities of what it's thinking. But if we wanted to, if I wanted to send this to a friend or a colleague, obviously I could send the notebook, but that's a little painful. But what we have in Wolfram language, we can literally just deploy this to the cloud. So all users are able to just host things on our servers, and we can go ahead and deploy this. What we've done here is we've created a form page where we are kind of doing some general data science, where we're creating a pie chart of the probabilities on our given Titanic classifier, where we are inputting that from this form. So if I wanted to go ahead and say I wanted to give this to my friend, and then he wanted to identify if somebody in third class who was 25 and male, whether they survived or not, they could just go ahead and do that, running that all just in the cloud on our servers. So, very powerful potential right there. So we also have, in the examples I've showed you, we haven't gone into too much detail about the algorithms, but to an extent, this is all done for you. You are able to specify the algorithm type itself. So if I wanted to do this with Markov method or gradient boosted trees, I'm able to do that. But if you are unaware, you can just go automatic or even go without it, and then it's able to go ahead and so what's done here, it's mapping these colors to individual 2D coordinates. And what is it used? It's used naive Bayes as a method. It's just chosen that for you. So it's just like an automated way of like automatically selecting algorithms for you. Something to bear in mind, though, different algorithm selection will lead to different performance. So this is kind of what this, when we choose nearest neighbors, we're going to get different outputs to when we choose support vector machines and kind of neural network type methods. So, right, when we're talking about, now we're going to talk a little bit more about neural networks itself. So neural networks are kind of like these multi-layered layers of regression. So where we kind of have these like individual neurons, which are kind of like working mapped similar to ways in the brain. And we eventually can do these like classifying, predicting tasks, but on a really big, powerful scale. So quite often categorize these into different formats, which kind of depend on how we kind of pass information through the network. So we've got feed-forward networks, convolutional networks, etc., etc. So we saw earlier the neural network repository. So you can just go ahead and search through many, many different like curated neural networks already, all in the Wolfram language, which is all pretty cool. So we can go ahead, as we saw earlier, we can just pull in those and then work on them within our notebook environment. So this might take a minute. Oh God, don't take that long. In fact, I'm not going to do that because I might not have time. So I'm just going to fix this. That. Okay, and yeah, we can go ahead and, but it's fundamentally the same thing. All right. Okay. So that's not showing. Okay, so I guess a little bit more into details about the individual layers itself. So you have a bunch of different functions available. So we can look at those, which are in networks. So yeah, a bunch of different high-level functions you have access to yourself. So general linear layers, we can compose neural networks in this very flexible way, which is all pretty cool. And yeah. So we can actually go ahead and get a bit of insights about the individual layers themselves. So, fundamentally, layers are in fact just kind of trainable models themselves. So, if I want to, it's just computing this kind of weighted sum in general. So what we can do here, we can create some data. And then if I want to go ahead and make a more kind of high level model for that, I can use this fit function to generate a function for this particular data set. And so I'm, kind of essentially just creating a, almost line of best fit for this particular data. So here I've got this data here, and then I've also got, I'm plotting the function we created from this fit function earlier. So we can go ahead and train a very simple neural network. So we could do that by, first of all, creating, like kind of doing some processing on the data itself. So we're creating these mappings from inputs to outputs, where we are so we've got this data initially, then we are doing this kind of map apply method. So we are changing so here we've got head of list, 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 list. So we are mapping over this entire list of lists. We are replacing this head with rules. So everything in Wolfram language has a head. If you want to, you can go ahead and look at the full form of that. So it is all rules. So we are effectively replacing, for every time we have lists, we are replacing it with rule of this parameter to this parameter. So that's what we're doing here. And then we can go ahead and create this linear network consisting of just one linear layer, consisting of one little matrix itself. So this, when we create this network, it is by default uninitialized. None of the weights and biases are actually learned yet. So we need to go ahead and do some training. So we do that with nettrain. And this is, kind of giving us a nice infographic about what's going on behind the scenes. So, we're currently using the Adam optimizer method, and we're getting this nice kind of infographic of how the nettrain function is, minimizing the loss function. So it's kind of, getting the, an accurate, able to accurately predict things eventually. So it does take a little bit of time. Kind of wish I was running this on a more powerful machine, but I'm not. Okay, cool. And then we have this trained neural network consisting just of this simple linear layer. And then we can go ahead and see how it's doing, creating the, predicting individual values for a input given data set. So we can go ahead and we can just like extract some of the weights and biases from the network we've just created. And it's kind of interesting to see how this is, fundamentally very similar to the coefficient list from the model we made, just using a very simple linear regression fit function. And we are able to get the same results. So we're kind of getting this same equation through the weights and biases of the function. So we're also able to go ahead and chain those layers together using netchain. But fundamentally, what this is doing is just applying networks to data over and over. It's kind of like this nested application of networks. But obviously, this is a nicer way of formatting it than doing network of value, of network, of network, of network, of network, etc. So let's go ahead and look at a bit more of a complicated example. So some nonlinear data where we've got this kind of kink associated to it. So what we can do here is we can create this, neural network consisting of a linear layer and then a element-wise layer of a ramp function. So this is pretty much sure it's just like a ReLU type function. And then we will finish it with another linear layer. Now, this will go ahead and create the network. Again, it's not initialized yet, so then we need to initialize it with some training. So let's do that. While that's waiting, I can explain a little bit more. So pretty standard neural network type building. kind of paradigm is to go for a linear layer and then a non-linear layer followed by a linear layer. You kind of need this like interspersing of linear layers with non-linear layers for the best results. So again, we're doing some more training. So we are, again, minimizing the kind of loss function to get more accurate predictions. So that's taking a bit of time. And again, if you wanted to train this on the GPU for fast network, then you could do, I think it's target device, target device. And then you have the option to train on the GPU or the CPU, but it wouldn't work for me on the GPU because I don't have a NVIDIA graphics card because I'm on a Mac. And then we can go ahead and see how the network has done on the, by drawing the prediction of the network on the actual same graphic as the original kink data. And you can see it's kind of learned the features of the data and it's able to do a reasonably decent job of prediction, which is pretty cool. And it's just gone from this very simple network that we've created earlier. So yeah, there's loads of different functions associated with neural networks. Many different kinds of layers you can create for your own things. In general, making your own neural network is a pretty complicated task, and with the neural network kind of repository, you are able to pull in these curated, predefined networks pretty seamlessly into your environment. So sometimes you do want to ask yourself if you really want to make a neural network because it's a pretty complicated thing to be doing, but it's interesting nevertheless. And there are a bunch of guides on creating neural networks in the Wolfram language documentation, which I would recommend checking out if you want to learn more about that. Right, okay, let's finish up with a bit of like exploring how we can integrate LLMs with Wolfram language. So we can kind of like just directly interface with an LLM. We can use this function LLM synthesize to go ahead and directly prompt an LLM and return the information into our notebook. So I've asked the LLM, in this case, I think it's GPT 3.5, to return a funny poem, which is pretty cool. We can also like kind of like programmatically interact with an LLM. So if I want to create a function which contains a particular slot, I can go ahead and define that, and then we are able to call that function we have defined with a particular argument. So in this case, I'm asking it to write me a funny joke about, in this case, I am doing apples, and it returns a incredibly funny joke, obviously. Other things we're able to do, we are able to kind of generate LLM tools. So these are kind of like little functions, or yeah, but I mean they are exactly that. They are just functions which the LLM can go ahead and use. So this is particularly powerful if LLMs are, whilst they're very cool, powerful technology, they're not good at everything. So one thing they aren't good is pretty like math type problems. So if I ask, what we're doing here, let's compute 4 to the 44, it's returning this 3 billion, which is not correct. We can even do that here. So we can be computationally, within Wolfram language, obviously it's going to be computationally correct. We're not relying on statistics to hazard a guess at what this is. We can actually go ahead and do the raw computation behind that. So LLMs here, not so great at being able to do this like arithmetic type problem. So what we can do is we can give it the option to use a LLM tool. So here we're creating a tool called run code, which runs Wolfram language code. And we are effectively turning that to an expression, which is going to be evaluated. So we are then pretty much doing this here. but within a LLM tool. So then we can go ahead and again using this LLM synthesize to generate a prompt. This time we are giving it the option to use this tool here. And let's give it a different example. So let's do 4 to the 49. It is able to go ahead and use that. And let's just double check that it's done that correctly. And it's able to match that correctly. Whereas previously, if we just asked it to do that, it's not going to be doing at all well. It's not going to get that correct. So yeah, it's just this nice way to seamlessly kind of augment the ability of your LLM within your notebook. Other things we can do kind of like data extraction type problems. So we can use this LLM example function where we are kind of almost feeding the LLM like auxiliary training data. So we're giving it inputs and we're giving it the expected outputs. So we're kind of telling it, given this string sentence, I want you to create this list of associations consisting of the name, the age, and how we're dealing with age within this quantity function, and with this height within this quantity function. So we can go ahead and create that example function, and then we can go ahead and use this name, age, height extractor on some new unseen data. Go ahead and have a look and see what it does there. And it's gone ahead and handled that in the way we've kind of told it to do so. Like, so it's this powerful way of augmenting the ability of your LLM within the notebook. And then we can go ahead and we can turn this into an expression. So we're able to call Wolfram language functions on it. And then we can use this dataset function, which we explored earlier. And then, yeah, we're just looking at how it handled. So also within Wolfram language, you have access to chat notebooks. So this is another way of interacting with an LLM within a notebook environment. So I could just, hi, a very simple example, can't think of much else to do, but it just gives you the ability to, if I wanted to write code, I can do that in the same environment all over, etc. Also, we have, this cool notebook assistant kind of thing, which is a new addition to the language. So again, it's a similar type thing where we've got this like LLM integration, but say it allows you to do more general type problems. So if I want to, if I wanted to see how I could plot 3D Julia sets, I could just ask that as a direct question, and it's able to give me the correct Wolfram language code. So it's a powerful thing for helping you to make particular Wolfram language functions or solve particularly Wolfram language problems. So we can go ahead and take that code and then evaluate that. And oh, it doesn't look like it's done that correctly. Interesting. What's it done there? I wonder if that should be an X. Nope. Okay, that's annoying. I think it's getting confused from earlier, actually. Okay, never mind. I think some of the context, it like remembers stuff from earlier, and I've run this already, so that's why it's not done correctly. But anyway, yep, so I guess to write some of this off, I would definitely recommend pointing you towards the Wolfram Language Documentation Center. So we have this, very nice documentation where you can learn about individual functions or parts of the language. Recommend checking that out. Also, Wolfram community, good place to ask questions if you have any. So general type problems. Again, we talked about Wolfram Alpha before. It's kind of like thing that was pretty popular a couple of years ago. I believe a lot of people got introduced to Wolfram through this. Also, Wolfram language type demonstrations, I'd recommend checking out. Just as things you can do with the language of so if I wanted to do some kind of like perceptron algorithm in machine learning, we've got this like pre-built in kind of things we can do. We can check out the source code to go ahead and look at that. I'd also recommend checking out Wolfram U courses. So these are kind of free courses where you can learn more about pretty much a very wide range of computational stuff. So if I want to learn some math stuff, I can go ahead and explore how data science is more than just statistics. And this itself is a event, but there are also general like courses you have access to. Okay, so that's what I've got for you today in terms of content to talk about. I think I've got 15 minutes to ask any questions if you guys have any. So if you have any.
So if anyone from the audience has a question, they can start asking. Well, Said, you can go ahead.
Thank you for your presentation. I have a question. Is it possible that I write a piece of code in Mathematica, for example, simple group basis computation via Burger algorithms, and then ask Mathematica to use it AI to optimize my code just by itself? Or is not still able to modify codes as input and return a new one as an output?
So you can definitely so with the notebook kind of assistant type things, one thing it is good at is asking it to optimize code. Um, I don't know about your particular problem. So it would be hard to know at a first glance whether it'd be able to optimize it. But I'm going to be hopeful and say yes. But bear in mind it might be too specific. But yeah, like asking the notebook assistant to optimize code is a thing you can do. So hopefully that answers your question.
Said, was that fine? And there is another question in the chat from Tachakon. If you want, I can read it, or you can read it yourself. It says, from what I understand, the Wolfram language is a high-level language designed to do things easily.
Mhm.
But what model does it use behind? That's the question. For example, tasks like image identification or classification. And is it possible to fine-tune that model or use an externally trained model?
Okay, that's a good question. So what model does it use? So it doesn't just use one model. So things like image identifiers. So, we were looking at earlier the image identification question. Where did it go? Image identifier. So this is powered by a unique model itself, and so you yeah, so like that's one particular model we're using. But what model does it use behind? And then, image identification or classification problems, we're kind of like building our own model itself. So that's what we're doing when we're using classify. Now this is kind of going to be using a bunch of different algorithms to build that model. So that's when it comes to image classification. Is it able to fine tune a model? Yes, it is. You can actually I think you can just operate on the model itself. So if I'm remembering this correctly, I can look at the individual layers. And yeah, so like I'm taking the first 10 layers of this model and so this is a model which I've pulled in externally. So this is the Google Linnet model, which you can just pull in from the resources. I think you can also import it as an individual structure. I can't remember off the top of my head how to do that. But basically, yes, you can take that and then create a new model. And then yeah, you can retrain that, and I would recommend checking out the documentation how to do that. I can't do it on the fly, unfortunately. But yes, no, you can fine tune an externally trained model. Yeah, good question.
Does anyone else has a question? Teresa, do you have a question? No. Hey, you are muted.
Hello. Well, first of all, congratulations. When you start, I don't know how involved you are in developing these things, but it's very, very nice. And yeah, when you started, I know Wolfram for Wolfram Alpha, of course. And when you started, yeah, I thought, why will anyone use Wolfram for machine learning? But you definitely proved the point. You have many interesting tools. And yes, I was in particular curious about this solving a maze. I don't know if it uses machine learning or is more. Maybe this is too far from your knowledge, but if it uses machine learning or is more like some reasoning tools or.
In terms of just solving a maze, I did speak about that, yeah. So are you asking, can you solve maze type problems using machine learning in Wolfram
So
language?
yeah, yes, I was asking if it well, it's more the other way around. I think I'm curious if Wolfram also uses reasoning tools, like I don't know, SAT or this sort of I don't know, more logic based reasoning, other than machine learning, or only uses machine learning.
Just for solving mazes?
Yes, for solving mazes.
That's an interesting question. I think, to be honest, I mean, solving a maze type problems, you're gonna have the ability to not, you don't have to use machine learning to do that, of course. Like there's a bunch of algorithms you can use. So yeah, it could be done in a range of different ways, but I guess with Wolfram language, it would be a nice, easy way to kind of implement a machine learning approach to solving a maze, or using other different kinds of approaches. So yeah, I don't have a good example on the fly right now. But yeah, fundamentally,
Yeah.
you could do that.
Okay, thank you, Git. I wanted to ask. Well, I mean, there are a couple of things I'm gonna check now. In particular, there was something like fine distribution and fine formula. I don't know if you know anything about it. I would like to hear about.
I mean, I could have a look off the top of my head. I don't know, but fine.
I mean, they were in the presentation that you gave.
Of fine distribution.
Yeah, or fine formula. I mean, fine distribution, I can kind of guess what it does. I mean, I will have a look at the documentation later, but
Yeah.
if you had any insights.
So I wasn't involved in the making of that. Are you talking about finding
Yeah,
this
like
bit here?
fine distribution, fine.
I don't remember.
Yeah, I'll have a look at the documentation. Just thank you for showing us all the different tools that Mathematica has. It's definitely very impressive.
Yeah, cool. No worries, no worries. Thanks for coming.
And yeah, looks easy to use.
Yeah. No, one of the nice things about the language is, I mean, I find this especially if I'm going from Wolfram, if I want to do something in Python, is just how like high level it is. So one line of code can do like so much. So I can, we had some nice examples where we like built entire classifiers, neural network classifiers. That would just be so verbose in other languages. And when I go to other languages, it's just almost a pain
Yes.
to write in them. But yeah, sorry, do we have any other questions? I'll stop talking.
No. That I was just agreeing with you. Yes, I think
Yeah.
that's a very nice thing about what you showed today.
Dr. Yassif?
Hi. So maybe it's more for curiosity. So sometimes I use the Wolfram Alpha, yes,
Mm-hmm.
or directly online, and let's say 5 years ago, I had less problems with it understanding not so formal questions like when I say integrate, etc. But lately, in the last months, I have more issues with it understanding exactly what I mean. Sometimes I need to write exactly the math in the mathematical language or in the Wolfram language, so for it to understand it. I don't know if it's because it's messing with some new implementation of artificial intelligence or some language model, which now I don't know. Is there something happening behind the scene?
As far as I'm aware, we haven't really done any drastic updates to
I see.
Wolfram Alpha. I'm like, so that's a different team. So
I
I'm
see.
not the best person to ask about that, I'm afraid.
Okay.
But
Okay.
that's interesting. You've been having different results. But yeah, sorry, I'm not able to
No.
give a good answer.
Thank you.